So, good morning everyone. I'm sorry I'll be doing this presentation in English. So first of all, thank you for taking my abstract for this prize. That was really nice of you. So this is a joint work between two labs, Promesse, as you can see, and Listen, which is a... so Promesse is a... comme ça? Ok. Désolé. Okay, so this is a joint work between two labs. So Promesse, which you might know as a solar processes lab, and Listen, which is a simulation as well as AI lab in Paris. So this work, entitled Fast and Accurate Field Reconstruction of Thermal Large Eddy Simulations by Deep Learning, was done by me as well as 4 other people, which are Adrien Toutan, Onofrio Semeraro, Lionel Matelin, and Françoise Bataille. So we'll be going through a quick context around the project and why we're doing this. The way we model solar receivers inside solar towers for next generation solar power plants. Then we'll be going through a quick general principles of machine learning, which are the basis of this work. Then we'll be going on to how we train the neural network as well as results and analysis, and conclude on these results. So, next generation solar power plants use air instead of molten salts, and this is a challenge because we need to know what happens inside the solar receiver for this new fluid. So, the way solar tower works is we have mirrors and that redirect the sun rays inside the solar receiver, and the key component inside this is the solar receiver. So the solar receiver is only heated on one side, as you can see on this sketch, and this implies extremely high temperature gradients. So the flow inside the solar receiver is turbulent and highly anisothermal in this case. And knowing that the thermal exchanges at the boundary define the energy efficacy of our system, it is then necessary to get the velocity, to understand the coupling between velocity and temperature inside our system. To do so, we have multiple tools in our toolbox, like DNS, which is an amazing tool, but is extremely expensive to use. DNS simulates all the scales of turbulence, but is extremely expensive, as said before. On the other hand, we have LES, or thermal LES in our case, which models only the big scales, but is mildly inaccurate for second-order statistics. Knowing that the heat flux defines the thermal efficacy of the system, it is paramount to get a precise heat flux for the hot boundary in our system. And knowing that from previous works, the heat flux is defined by the small scales. This is an image on the left of the heat flux at the hot boundary. It is necessary to develop deconvolution methods in order to get the heat flux at the hot boundary. It is also necessary to develop these techniques to try to compare LES fields with DNS, because we do not have a way to compare them if we do not do reconstruction, especially for their RMS, which is a quantity of turbulence inside the flow. And the RMS of the heat flux also gives us the thermomechanical constraints inside, or gives us a way to simulate the thermomechanical constraints inside the receiver. So these quantities are extremely important. The way we simulate what happens inside our solar receiver is extremely simple. This is the simplest modeling case. So it is a biperiodic plane channel flow with 2 periodic directions, so the direction of the flow and the direction of the span-wise direction, sorry. And the wall normal direction represents the heating, the asymmetrical heating inside the solar receiver. So the hot wall represents the wall that is subject to the concentrated sunlight, and the cold wall represents the insulated side of the receiver. This is important. The fact that we have a regular mesh in the x and y directions and that it is periodic is extremely important, because we use this for training our neural network. And in the wall normal direction, we do not have that. The height of our channel is approximately 30 millimeters, so it's extremely small. Now let's go on to general principles of machine learning. So machine learning generally amounts to training algorithms to recognize patterns in the data and then make decisions onto data that resembles the data used for training. This takes the form of a nonlinear optimization problem, where the data is, we input data that is that we have, and then we obtain data that resembles some label that we assign. This generally takes the form of stacking different layers with nonlinearities in between them. And this has many, many applications like image recognition, image generation, fraud detection, text translation, and so on and so forth. We will be presenting what a convolutional neural network is in here. So here I put a rough sketch of a neural network layer. So the blue image represents an input image to the layer. What is learned is the convolutional kernel, so what is in gray. And the green image is the image generated by convoluting in such a way. Let's now go on to the training process of our neural network. So it is important to know that while doing large eddy simulation, the filter that is used by modeling large eddy simulation is not known. So trying to invert it by knowing the filter is impossible, or almost impossible. So the aim of this method would be to try to find an inversion operator, which in our case takes the form of a neural network. So we chose to take the neural network output as a correction to the large eddy simulation field, such as it gives us the small scales. And here is an image of a large eddy simulation field. The neural network architecture we take is a multi-level architecture with multiple levels of the mesh. So to give you a rough idea, let's say you give a 3D field of 16 points cubed in entry here. Here is going to be 8 points cubed, and here is going to be 4 points cubed. So this is a multi-level architecture because turbulence is fundamentally a multi-level physical phenomenon. And here I've put the sketch of convolution before, to understand that this is a fully convolutional neural network architecture. The way we acquire our data is by, first of all, taking a DNS at mean frictional Reynolds number of 180 and fixed Prandtl number of 0.76 after statistical convergence. From this, we take 17 time steps spaced by this scaled time step. We then interpolate the data onto a coarse grid, an extremely coarse grid actually. We go from this grid, which is approximately 400 by 400 by 300, into a 50 points cubed mesh. And this step actually keeps the statistics of the turbulence, which is extremely important. And then we filter using a top hat filter. And the two last steps, so this is used as a label for our neural network, and this is used as the entry of the neural network. We benchmark our results against another well-known method from the literature, which is the von Serret method, which essentially is just a Newman series over the filter used for the LES. So this supposes a knowledge of the filter, which we in general do not have. The way we manage our data is we learn over, so we split our data into 13 time steps for training and 4 for validation. So validation is a step that is used to see the performance of the neural network over data that it did not optimize over. And one tests the step after the training to see how the neural network generalizes to cases unseen and that are slightly different from what was learned. The way we learn is over patches. So patches are cuts inside the space. Instead of taking the whole domain, we take different patches in space, which are local of size 16 cubed. And because we have periodic directions in our flow, like I said before, we can do rotations in these directions, as well as axis flips, because the neural network should not have any preferences towards any directions. And this gives us approximately, for each height in the canal, because we fix heights while training, approximately 950 different training crops that we can take. This is a sketch of how the neural network learns. So we take an LES and a corresponding DNS field. We take a cut into space of 16 points cubed. Then we ask the neural network to reconstruct the LES. and we optimize our neural network with regards to the label. And this is done only for one, this example is only for one height in the canal. We then sample inside the whole, or we increase the domain in which we can sample from. We first sample closer to the hot boundary, and we procedurally increase the way we sample in space until having the whole domain, as set on the right. And this enables us to learn over harder and harder data distribution, since we have a relatively lower friction Reynolds number on the hot side, whereas we have a colder Reynolds number on the cold side. This is the error function of the neural network as it's training. So as you can see, you have jumps inside this error function. This is because we increase procedurally the domain in which we learn, we let our neural network learn. And we can see that even though we have jumps, the neural network manages to quickly learn over the training and generalize over the validation data, which resembles roughly the training data. These are cuts or slices inside the space. So we took 3 slices, one closer to the cold boundary, which is on the top, one closer to the middle, which is in the middle actually, and a third one which is closer to the hot boundary. From left to right here is the DNS, so this is what we want. Here is the LES, this is what we have, or the input to the neural network. This is the neural network output, and this is the literature method. So as you can see, the neural network manages to learn how to reconstruct the DNS small scales, even though there are some spatial gradients which might be too high, but this is still an acceptable result for reconstruction. The von Siret method, on the other hand, seems a bit blurred with regards to this. This is another time step as an example. This is yet another time step. You can see the difference slightly here. And this is the last time step we took to show here. Then we have some RMS values. So as said before, RMS is the quantity of turbulence in each height of the canal. And we can see that the LES filter actually squishes the amount of RMS in the domain. And we can see that both the neural network and the von Siret method manage to reconstruct the RMS pretty well, even though we can see this slight overshoot right here on the right, closer to the hot boundary. But this is still, this can be mitigated through other means. This is for the test time step. So as said before, this is a time step that is taken further into the simulation. You can see that the reconstruction method actually is also acceptable in this case, but we can also see some slight overshoots in spatial gradients. And this is the same plot as before for this time step, for the test RMS time step, and we can see the same phenomena happening. Let's now go on to the PDF, or the density of our data. We can see that, so from top to bottom is the different slices. So to remind you, the first slice was closer to the cold side, sorry. This was in the middle of the canal, and this was closer to the cold side. So the LES filter in this case, we can see that it squishes also the distribution of the data to the middle of, or to the mean of the temperature at this height, right? And from left to right, we can see that this is from different time steps. So this is for the different validation time steps, and this is for the test time steps, sorry. And we can see in here that the neural network actually outperforms slightly the literature method because it manages to stay on the DNS, whereas the literature method slightly overshoots in the middle, as can be seen here. Let's now conclude on to this work. So we can see that this method manages to reconstruct the small scale, and actually small scales taken from LES, and actually generalize over unseen time steps during training. We can also see a slight overshoot of spatial gradients and overshoot over the RMS values, but this can be mitigated through a mild convolutional filter after the super resolution step. And this is a generally good method for the study of high temperature solar receivers. Future work will mainly go over learning different meshes. This work was only done for one mesh. Learning over the distribution of the data, because this, the way we learned here was using labels. and generalizing over different Reynolds numbers, which is pretty much the hardest task in all of these future tasks. Thank you for your attention.
Y a-t-il des questions dans la salle?
Sylvain.
Oui. Merci pour la présentation.
Merci.
Je sais que tu parles bien français.
Oui, je parle bien français, effectivement.
Alors, donc je vais continuer en français.
Très bien.
J'ai pas bien compris la différence qu'il y a entre ta méthode neural network
Oui.
et la référence biblio là, de
Van Sirat, ouais. Alors, la référence, alors le réseau de neurones, ce qu'il fait, lui, c'est qu'il reconstruit à partir de données qu'il a vues lors de l'entraînement. C'est-à-dire que, et lui, en fait, il apprend à reconstruire en corrigeant la LES. Et donc, finalement, on peut lui passer un peu n'importe quoi. On peut lui passer un champ de LES qui a été simulé au lieu de prendre un champ de DNS qui a été filtré. Alors que la méthode Van Sirat, qui est là, en fait, elle suppose une connaissance sur le filtre, que nous, on n'a pas. On ne connaît pas le filtre de la LES. Donc, cette méthode-là, certes, fonctionne quand même pas mal, mais dans le cas où on connaît le filtre. Voilà. Dans le cas où on ne connaît pas le filtre, bon.
Ok.
Y a-t-il une autre question?
Oui.
Sur la diapo suivante, la 16, vous donnez la 13 pour l'apprentissage et uniquement 4 pour la validation. Comment vous avez choisi ces deux chiffres? Parce que le rapport 13 et 4 me paraît faible.
Bien sûr, il n'y a pas de souci. Donc, alors c'était pour avoir un entraînement rapide et avoir des résultats rapidement, surtout. 4 de validation, en fait, si on regarde par rapport aux différentes découpes qu'on peut faire dans l'espace, vu le volume des données, c'est des données 3D et non 2D, parce qu'on peut voir, par exemple, pour des entraînements en 2 dimensions, pour du traitement d'image, des datasets qui sont beaucoup plus gros, mais en fait, quand on regarde seulement là-dessus, et qu'on multiplie là-dessus, ça fait à peu près peut-être 1400 différentes découpes possibles pour différentes hauteurs. Et donc, vu qu'on a 52 hauteurs différentes, en fait, ça fait qu'on multiplie par 50 ce nombre-là. Donc finalement, certes, c'est pas beaucoup de pas de temps, mais c'est un volume de données qui est quand même assez gros. Oui, exactement.
La question était plutôt sur le rapport pourquoi 13 pour l'entraînement et 4 pour la validation.
C'est parce que c'est en règle générale en apprentissage, ce qu'on fait, c'est qu'on prend 80 pour l'apprentissage et 20% des données qu'on découpe pour entraînement et validation.